Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to the latest installment in the Black Hat Webcast series, Hardware Hacking Party Tricks, Techniques for Exploring, Manipulating, and Exploiting Embedded Systems, brought to you by Black Hat and Informa. I'm Steve Paul with Black Hat. I'm your moderator today. We have just a few announcements before we begin. This webcast is designed to be interactive between you and our presenter. Later in the program, we'll ask for your feedback. We strongly encourage participation and are happy to take your questions and comments. You can participate in our Q&A session by asking questions at any time. Just type them into the Q&A text box in the bottom left of your console. We'll answer as many questions as time permits after our presentation. Slides will advance automatically throughout the event, and a PDF copy of the presentation is available at the bottom of your screen in the resource box. At this time, we recommend you disable your pop-up blockers. But if you're experiencing any technical problems, please visit our webinar help guide by clicking on the help ? Icon on the bottom right of our console. If slides are not advancing, please press the F5 key on your keyboard to refresh your browser. And now on to our presentation, Hardware Hacking Party Tricks, Techniques for Exploring, Manipulating, and Exploiting Embedded Systems. Today we're going to hear from Joe Grand, aka Kingpin, computer engineer, hardware hacker, and founder from Grand Idea Studios. Joe, over to you.
Hello, everybody. Thank you for coming. My name is Joe Grand, and we are here to do some hardware hacking. The name is a little bit incorrect. You know, party tricks typically are things that you show off at a party and they don't really have any real use. But I liked the name, and the demos that I'm going to be going through today do have use. I'm kind of ranging from beginning sort of hardware hacking steps all the way to more complicated, more advanced techniques. And as you'll see, they range in complexity, even as far as just getting it set up and then the end result. So it's going to be a lot of fun. The real goal of this presentation is to just get people inspired about hardware hacking. If you've never looked into hardware hacking before, you'll be able to see a little bit of that process of how we go through and look at a piece of hardware and the different kind of tricks and techniques we can do against the hardware. And then if you are involved in hardware, maybe there'll be some tools that you haven't seen before, right? We're going to start off slow, and then we'll get up to other things. The talk was really inspired by some demos I gave at Black Hat Tools Arsenal a couple months ago, where we were doing these live demos. And we thought it'd be really fun to do a lot of live demos, because everybody loves live demos. And I'm sure a lot of people like when the live demos fail because it makes the presenter awkward. But hopefully that's not going to happen. I do have backup videos in case, everything goes haywire. But I have a series of live demos that I'll switch between my camera here, which is going to point at some of the electronics. And then I'll switch over to my screen sharing to see the actual programs that I'm running on the computer. So there is a delay as I switch between the different screens and cameras. So we'll just, that's a good time to actually have a little drink. And I forgot, this is my Black Hat cup of kombucha. And with that, let's get started. So this is sort of the hardware hacking process. If you look on the slide, we don't really follow this for all of the demos necessarily, but this is the process that I go through every time I look at a piece of hardware. No matter what it is, I tend to follow this. And it's funny because being an engineer and a hacker, from the hacker side, you always hear, oh, you think outside the box, you try new things, blah, blah, blah. But then the engineering side of me is a very rigid and kind of process-oriented and precise. So I combine those together and follow this process, but then within that, I'll branch out and think more of the attack and think more like a hacker than an engineer. But yeah, so just looking at this information gathering, getting as much information as you can about the product, whether it's example code, documentation from the vendor, previous work that's been done, just to get as much knowledge as you can before you start messing with the product. Product teardown is the next thing. That's you get access to your physical device, you take it apart, you look for the main components on the board, you look for part markings on the board to identify areas that might be interesting to then do some of the stuff that we're going to do in our demos. Buses and interfaces is a section where we're looking at inter-chip communication buses. We're looking for activity on the board. We're looking for interfaces like a programming interface or a debug interface like JTAG or a UART interface, or maybe it's some interchip communication like I2C or SPI that we can tap onto. And a lot of times, as you'll see, engineers are not really thinking about the fact that somebody is going to listen in on what's going on their board. And if we can do that, we get all sorts of information about what's going on, and then we can exploit that as well. Memory and firmware is another level down. That's trying to get access to data off of memory devices, whether it's firmware inside of a microcontroller or external data on an external device. And then firmware, of course, a lot of times electronic systems, embedded systems are really just general purpose computers running some specialized code. Once you get that code out, now if you're a software hacker, you can use all of these reverse engineering tools, static disassembly tools, dynamic disassembly tools sometimes, to figure out actual complete program operation of what's going on, and then maybe patch things and throw it back in and reprogram it and do whatever from there. So that's kind of the next level. And then we get into more advanced stuff, fault injection, side channel attacks. I will show some examples of that at the end. So, we kind of do some sprinkling of this process throughout this presentation, or I guess demonstrations, I should say. So here's our plan for the day, a little party plan. So again, we're going to start off with kind of the more basic types of techniques and advance through. And it's a little bit like a cooking show. Like I already have my demos pre-wired up, so I just have to plug them in and make some connection things, and hopefully everything will work. But it is that way. A lot of that legwork has already been done. So some of these demos might look really easy, but in reality, when you're actually building something from scratch, it might take you hours, days, weeks, months, depending on the complexity, to get to the point where you can then do your attack. And then even at that point, you kind of keep your fingers crossed to see if it actually is going to work at all. So a lot of times you want to take what you see with a grain of salt in my presentation and just in any InfoSec presentation, because when you take something that's been presented and then replicate that work or try to use that work, there is a lot of that underlying work that has to be done. So we'll start with visualizing signals, which is just a way to be able to see what's going on in a system. We'll talk about UART, a little bit of memory extraction. We'll do some stuff with JTAG, which is an industry standard debug interface for identifying pins on a board and then using those to do some cool hacking. Then we'll go into glitching, which is fault injection, and then electromagnetic fault injection, which is sort of like black magic as far as causing corruption and misbehavior on a board. So lots of different things to do. So we're going to start off with visualizing signals. I'm going to switch over to my GoPro, which I'm using as the camera to show the electronics. And then you're not going to see my face again until we open it up for questions at the end. So you can type your questions now. I'm not going to be able to see them because I'm doing all this other stuff, but you feel free to ask questions and we can revisit all of those. But yeah, so I'm going to switch over to the camera, and then I'll end up switching between the camera and my screen for screen sharing. So here we go. BRB.
He'll be right back.
Okay, here we go. Am I back? You can see.
Go for it.
Cool. Okay, so what we have here, this is going to be our little test area, demo area. And the first demo I have set up, this is a Cisco Linksys WRT 120N, so little access point, just to kind of show, there's lots of big components on here, so it's easy to kind of poke around. But really, one of the first things that I'll do, and why I show it here, is I like to look at a system and poke around with a tool like an oscilloscope or a logic analyzer to help me understand what activity is happening on a board, what signals are doing things, what aren't. And an oscilloscope, the one that I'm using here, this is a bench top high-end oscilloscope. It's obsolete now, but still was fairly expensive. And but you don't need a super high-end tool. You can get away with a logic analyzer as well will work. There's a lot of open source tools. One of them is the BitMagic Basic. There's a lot of other sorts of very simple tools that will work with some open source logic analyzer software called SIGROC. This is just my go-to tool. And the point here is to just identify signals. So an oscilloscope and logic analyzer is going to let you visually see signals and how they change over time. And that's pretty wild. If you just look at a circuit board like this, there's stuff going on all over the place. There's signals being sent, but we can't see anything. But with our scope, we can. So let's see, we'll just get this set up. Like with every tool when you're dealing with electronics, you have to identify a ground connection. And ground is really the 0-volt reference, this kind of shared reference. I've already done that, and I've marked it on this board. Generally, if you don't know what it is, you can look at the power supply section or look for the negative side of a capacitor or look at the data sheet for some of the components to figure out what that is, because it will tell you. But we need that so when we're monitoring signals or injecting signals, we're all at the same common reference. So this system is already on. And usually what I'll do is I'll look around and say, okay, like this area is the power supply in the upper corner, so I don't really care about that. But I'm looking for the digital section, and I see some wireless stuff here. So I'm just going to kind of use my oscilloscope probe and just move up and down on all of the different pins, just to get a sense. So I see this one is, let's see, this one's logic level high. It's just sitting there. A lot of times we're just going to see kind of static state, nothing going on. But I would end up making notes of this. And you're probably asking, like, well, what's the trick? The trick here is that we're actually visually seeing what's going on in a system. So that's pretty cool. Of course, we're not seeing any real activity yet, so not as exciting. Let's see if I can just scan my, oh, okay, so here's one. And I am just randomly doing this. I haven't prepared this in advance or anything. So here I see a signal. Let's see if I can kind of slow it down a little bit, go into a better time division here. So it looks like it's some sort of clock signal. Let's see, can I do like a quick measurement? So it's a 40 megahertz clock signal on the system on a chip, which is the main chip that's running. So maybe that's the heartbeat for the system that's driving the system. That might be useful to know if we want to do some sort of clock glitching or fault injection later on, because we can use that and inject our own kind of glitches or own heart palpitations into that heartbeat. Let's see what else. I'll just kind of move around some more. There is something. I do have a plan for this, by the way. So yeah, we would make note. Down here we can see there's like the RAM, and this is going to be connected to the microcontroller. So it doesn't look like we see much going on the RAM right now, at least on the pins I'm looking at. And I'm just scraping my probe around. I think over here, this is like the wireless chip. Oh, there's another. Okay, so another 40 megahertz signal for the wireless chip. Now, one thing to keep in mind is a lot of times the things that we're interested in, and in this case, what I want to look for is some sort of boot log information, because that's going to bring us to our next demo. That type of stuff really happens on power up. So when we're dealing with a system that we don't know, we want to make sure that we not only run it in this state where it's already powered up, but we want to start looking at signals and then plug in the board. Because on power up, we're going to see a lot of activity. So let's actually go ahead and do that. This device here is a type of serial flash device. I'll talk about that more later, but that's really common for systems that don't have their own internal memory. So the firmware is going to be stored on a device like this. I bet you that if we look at that signal coming from that memory device to that system on a chip on power up, we're going to see activity, because generally the code gets loaded into the system on power up. So I'm just going to pick one. I don't even know what line is what, but I can kind of see on the board the trace going from one chip to the other. So I'm just going to hold it onto pin 1. I'll plug this in and see, like, do we see anything? Oops. It would help if I was touching the thing. Okay, so we see something, but now I'm going to need to make some adjustments on my scope to actually capture those. Wasn't a huge amount of data. It changed my triggering level. So a lot of times it takes some effort to kind of get there. All right, let's try that again. Let's power cycle and see. Do we see anything? Okay. So I don't know if you can see the oscilloscope screen, but we see a lot of information being sent across. That looks very clock-like. So that's probably the clock line, and then there's going to be an associated data line somewhere on the actual chip. that is synchronized to that clock. So if we wanted to like sniff the data off of the device on power up, we could probably do that. Down here, this connector here, another thing that when you're looking at a board, just kind of preliminary view, is you're looking for connectors, things that are intentionally meant for engineers or for manufacturers. And I had soldered these connectors on the board. Normally, those would just be unpopulated. And those are going to be things where your eye would be drawn to those and say, oh, OK, if the engineers intentionally put those things there, they're probably interesting. So on this connector down here, this is another one that I'm interested in. So I'm going to hold my probe there while I power it on. And again, we're generally going to see information on power up. And that's what I'm trying to do here. So we can see some activity here. This ends up being what's called the UART interface. And we might not actually know that yet, but if we look at the signal, we can see, oh, everything is kind of an even multiple of each other. And that's a good clue that it's an asynchronous data stream. And I'll get to that in a little bit. But what we can do here is actually manually measure the width of 1 bit. And that's going to give us a good clue about what type of signal this is. So what do we see? So we have about 8.6 microseconds for the width, maybe a little bit less, kind of off here. Let's see. Yeah, 8.5 microseconds, which is the time it takes to send 1 bit from this system. If we invert that, it's 116.55 kilohertz, which would be a 115.2 kilobits per second UART data stream. We can verify that also on our oscilloscope before we move on to being able to visualize it a little bit better, where we can enable our serial decode functionality. I know it's a little bit hard to see on the camera, but trust me. And now we'll run the system again, see if we can get a good kind of chunk of data. I'm actually going to put my clip on here so I don't have to hold it in place. All right, so let's power cycle the board. See if we can zoom in here. Did I change my bus configuration? Let's see. My baud rate is wrong on my oscilloscope. So once we measure that bit width, we can set it to 115.2 kilobits a second. Sorry, we'll run that again. And we should be able to see some actually like human readable, interesting text. So here we go. There's like a lot of information here, but it's in a way that it's really hard to see, right? It's kind of flying by. We might be able to do it in some sort of like listing way on the oscilloscope. But that's not really the point. The point here is for us to probe around on the board, identify something that might be interesting to us, and then use the correct tools to actually make sense of that. So that's our visualizing signals, just to get some idea of activity. Now, knowing that, especially in our case, we know there's a UART interface here. UART, again, is an asynchronous serial communication interface, very, very common because it's generally going to be a point-to-point type of system, and it's usually an interface that a target board will use to transmit information to a human, and a human will use to communicate back to a target board. You do see UART for chip-to-chip communication as well, sometimes between different systems, and there's been some attacks against systems that have done that. The one that comes to mind is Colin O'Flynn had given a talk about, I can't remember the name, it was at Black Hat, it was like hacking like a movie star or something like that. And it was a key electronic lock, and the keypad was actually sending UART data, asynchronous data, to the rest of the system. So he could just emulate that. And there's been some other ones with like some authentication tokens and stuff. But generally, UART is used a lot for this human connection to a board. We'll see boot log information like we'll demonstrate. We'll see access to bootloaders. Sometimes we get dropped straight into a root shell on devices. So even with something very simple like a UART interface, we can compromise boards if they're not designed properly. So I'm going to switch out. I'm going to turn off my scope so it's not making noise in the background. Switch out my probes. Go to the next one. So disconnect this one, throw this one off to the side. So now I have another access point here. This is a, what did I write? Oh, it's a TP-Link TLWR841N. Now, the reason I'm using these is because they're so common, and if you want to get into hardware hacking, you can go to Goodwill, you go to a surplus store, you can buy these things for $5, $20 or whatever. all day long, and you can hack on them and get more. And it's a great platform because things are exposed. There's different types of memory devices and stuff to play around with. And generally, they're all running some sort of Linux. So you'll have a UART interface. You'll probably have a JTAG debug interface that you can hack on. And a lot of the community has been working on different types of access points and routers to reprogram them with open source hardware and all sorts of other stuff. So really kind of cool. All right, so I have this board here, and I already have the UART interface identified. What I'm using to communicate, or sorry, to convert the UART data that we were seeing, say, on the oscilloscope, which is just passing by really fast and kind of hard for us to read, into something more useful, is a USB to serial adapter. So this one is called the FTDI friend. This is going to take in the UART data from the system, convert it to a virtual COM port, so we can plug that into our computer. That's going to show up on our computer screen. We can have a terminal program running. And then instead of just seeing data come across the screen really fast, we'll see it as it was intended to be printed on the screen. So let's just go and plug this in. Luckily, I can use the same power supply that I was using for the other one. Let's see, get my FTDI friend plugged in. So even before I switch over to the screen sharing mode, when I turn on, actually, let's see. I want to enable the device in my terminal program so you can actually see what happens on the FTDI friend. Okay, so when I turn this thing on, it's probably going to be a little blurry, but if you look, you're going to see activity on the FTDI friend. It's blinking green on one of the LED indicators, which means it's receiving data from the target and sending that over the system. If I was hitting keys back, you would see it on the red LED coming up. So even without having a terminal program, if you can't even see it, you can still visually identify, like, okay, data is being sent. So that's the setup. It's pretty easy. I have my ground connection, and then I have my transmit and receive pins. If you don't know which pin is which, generally a UART interface is going to be pretty easily identifiable if engineers put it in an accessible way. You usually see a 4-pin connection for the power line or system voltage line, ground, transmit, receive. Maybe you'll see test points instead, which are just copper pads on the board. You might even see some silkscreen markings. So on the board, there's white lettering. Sometimes it's going to be other colors. And engineers put that on there to help them identify what parts are what on the board to make it easier for testing and debugging. So it might even say UART interface or transmit or receive. If you don't know, though, if you identify ground and you identify one of them you realize is the system voltage by following where it goes, then you just try one orientation of the other pins. If it doesn't work, you just flip them around. If you don't have a scope to probe around first. Okay, so I'm going to switch over to my screen share so you can actually see the data that we're seeing on PowerUp, and we can kind of mess around with that. So be right back. All right, looks like we see it. Okay, so right here, I just have my terminal program set up. I have it pointed to hopefully my computer didn't just crash with all of the windows open. Come on, computer, you can do it. Steve, are you seeing anything on your end, or is it just really slow?
So I'm not. I'm just seeing a white blank screen there. So you may need to close out of something that you don't need, or maybe even refresh your browser. While you're refreshing your browser, I'll just remind the audience we're getting a lot of great questions already, and we'll answer as many as we can at the end here. So yeah, close out, try to refresh. You got a lot going on.
Yeah. It looks like it was just the terminal program. So what I'm going to do is I'm just going to, let's see if I can load up CoolTerm again. And do you not see my screen, or you do?
I see kind of your desktop, so I see the Sahara.
Oh, great. Okay. So, all right. So I'm reloading the terminal program, and we'll see if my computer decides to act up or not. Actually, let's see. While that's loading, I will take a look at a question. I love live demos. Oh, there's a lot. Okay. Okay, so CoolTerm seems to not like things anymore. I'm going to switch over to another view. I have a terminal program here called PuTTY, and I should be able to use that to also communicate to the USB to serial device. I just need to check what the COM port is. Okay. So let's see if this one happens to work instead. Right, so I have my serial port set up, FTDI friend. Let's see if we can open. See if I can make this a little bigger. I don't know how small the text is going to be. And OK, so I can see data. All right, so here we go. So I think we're back. And my CoolTerm is still trying to load on the Mac. That is funny. OK, well, I'm just going to let that keep going. OK, so I'm going to power up this access point now, and we should be able to see all of the data coming from this system on power up and see what we see. So text is a little bit small, but we see all of this boot log information that this is the similar type of stuff to what we just saw on that other access point. It's booting into Linux. It's giving us all sorts of information about the memory layout as it's loading through the bootloader and loading different parts of the system. And then once it loads, now we actually get to a login prompt. And here is like, I think I tried logging in as admin, which is the default password. And that's incorrect. I think I tried root password. So we don't know what the actual password is set on this particular device. That really doesn't matter if we're hacking a system, because we would end up doing probably going in through JTAG to modify the memory, which we'll do as a demo later. But I don't know if you noticed on here, early on, we see here it says auto booting in 1 second. So there's actually a bootloader on this system that we can pop into and abort the boot process and then get dropped into a bootloader and do some really interesting stuff. So let's see if we can do that. Let's power cycle the system. Now for TP-Link devices, when you get to that point, you have to type in TPL really quickly. So let's see if I can do this while I'm turning this on, make sure I'm in the right window. So now we're going to watch the screen. It says auto boot. I type TPL, and now we're in this WASP, W-A-S-P, bootloader. So we've interrupted the boot process. From here, there's a whole bunch of commands. We can, let's see, get version information. We're in U-boot. We can print the environment variable. So these are things that are going to be called as the system's loading. Maybe there's going to be interesting information here. Ethernet address, we see, oh, there's TFTP as well. So TFTP boot. We can actually use the TFTP protocol and load our own custom code into this board with no authentication, no nothing, by using this command. So it's a great, something for engineers and manufacturers, very helpful. But if this type of stuff is open on a system for anybody to use, that can be really dangerous. And in this case, actually, that TFTP boot command is used for people to load DDWRT, the open source access point tool, onto the device. We can also display memory, which is kind of cool. So let's try. It looks like I think memory starts at 8. I don't know. I'll just pick a guess, 8 million or something like that. Nothing useful there. How about it just at address 0? So we can go through and actually view different memory address locations. So this might be something where maybe we manually go through and dump the memory this way if we want to. In this, there's other ways to do it, like I'll demonstrate. But just the fact that we can do all of this stuff through a very simple UART interface is pretty cool. All right, so let's hop over. I'm going to go back. Let's see. Oh, I can just end my screen share, and that should go back to my camera. And we'll set up the next experiment. OK, looks like we're good. So I'm going to exit PuTTY, which I don't, nope, you're not seeing anyway, so that's okay. I'm going to exit PuTTY, disconnect this unit, get this out of the way. Oh, I didn't mention, actually I kind of did mention. So a lot of these systems are using these external SPI flash devices. So a very simple serial communication interface, and the firmware a lot of times is stored on a device like this and then gets read into the CPU on PowerUp. These memory devices have no encryption capability, no authentication, no nothing. They're what I call dumb memory devices. So we can, with the correct tools, extract the memory contents from that device without having to use, say, that bootloader and type stuff over and over again. We can just use it with a tool like a device programmer. And here, I'll switch to the slide also, which is our next party trick, is extracting memory contents. There are a lot of different methods to extract memory contents. Again, there are open source tools. So I'm using, this is a TL866 2+. You can get them on eBay and AliExpress and some other places for about $50 or so. I also have a Zeltec 501S, which is more of an engineering, not necessarily production model, but like a more of a high-end model device programmer. These will support 100,000 different types of devices or something like that. But if you know the particular device you're working with, you can find some open source tools as well. One of them we're going to be using later on, and I'll show some examples of other stuff that you can do it. But if you know the protocol, you know the memory device, you can use a tool, a software tool like FlashROM. We'll read some of them. There's actually some open source code for this device as well, because this is a Windows tool, as you'll see. So yeah, there's a lot of work in this space, but I figure doing this stuff so much, it's like I just want a tool that's going to do the job for me and not have to mess around. So getting a device programmer is a highly worthwhile investment, because then you make sure the device programmer works with the memory device you're working with, and you're good to go. OK, so what we have here is the device programmer. Normally, these are intended for you to take a chip off a board and plug it into the device programmer. But since we're hacking on stuff in circuit or in situ, however you want to call it, we might not have the capability or might not want to take the part off the board. There are certain parts that are ball grid array, BGA, which basically, instead of having pins, visible pins on the chip, everything is connected underneath the part. That's going to make it really hard to deal with. So if we can read chips in circuit, that's a lot better. And generally we can, as long as there's no bus contention or no contention, basically meaning as long as nothing else is trying to read that memory at the same time, we'll be able to connect to it and get the contents off. And like I mentioned, generally systems are going to read that device on PowerUp. We can just wait till the system boots up and then read the code off. If it's something where the system is constantly talking to it, then we have to do some tricks of maybe disabling the clock or holding the device in reset or whatever, which is a talk for another day. So I have a little hacked together, a little adapter here, which I have this little clip. This clip is called a dip clip or an SOIC clip. This is going to clip on directly to my target chip. And then it's just a one-to-one matching of the pins from the chip to the device programmer. What I'm using for our example here, I could have done it on any of the other ones, but I thought it'd be fun to use different stuff. This is a Low5 R1. It's a RISC-V based device that uses a Sci5 FE310 chip. And then the code, the bootloader and the code is stored on this external chip. This is also really cool because it's a low-powered device, meaning we don't have to worry about powering it externally before we use our device programmer. The programmer has enough current capability to read the chip while it's still in there. So I'm going to clip this chip onto the individual pins, and we'll see if that works, because the device programmer tool will actually give us an error if there's a pin that's not making a connection, which is good. So I'm going to plug that in. And now I'm going to switch over. Let's see if I get to my right screen. I'm going to screen share my Windows 7 virtual machine that has the software for this particular device programmer on it. I like how it just switched to like everything else on my desktop. So cool. Hopefully you all didn't see like stuff you weren't supposed to see. Okay. I'll hear about it later. Okay, so here's my Windows 7 virtual machine. XG Pro is the software, so I'm just going to double click on that. And load this up. So again, this is a tool that's intended for reading and writing different types of memory devices. So it makes it very easy for us to go, okay, let's choose the chip that we want to read. In this case, it's already selected. It's this IS25LP128 in the SOIC package. And that tells the device programmer what algorithm to use to communicate to the chip. The way that I knew the chip is I looked on the circuit board and I could see the part markings on the chip, and it tells me what it is. Or if you had a schematic, or maybe you would have to work that out by some educated guessing of saying, oh, it looks like a memory device, but there's no part numbers on there. I'll give it a try and see if I can automatically identify the correct pins. So we've chosen the correct thing here. It actually gives us some information here like, okay, chip type EEPROM, which is the type of memory inside of the chip. We call it SPI flash. I'm not sure actually why it's mentioning that, but IC size 16 megabytes, which is actually really, really big for an external device. So I think it takes a little while to read it. And then right now it's blank. All Fs means we haven't read anything yet. It looks like we're all set up with our programmer. So all we need to do now that we're clipped on here is click the read button, and let's see what happens. Okay, so it's saying read the flash, read the status. I think that might, I don't know. Okay, this is saying use an adapter, but we've used our own type of adapter. And we just do read, and we don't get an error. So it's good. It says pins detected passed. That means our clip is actually working properly to make contact to the chip. It's read the device ID from the chip, okay, which is what it expects given that part number, and now it's reading the flash. So now we can sit back, have another sip of our kombucha in Black Hat mug. And we wait. So yeah, sometimes though you're gonna plug into a system and it's not going to work. Usually you want to power a target system separately and then not attach a power line from the device programmer to the target board, because you don't know the power requirements of that particular system, and generally test equipment isn't going to be able to power that. But I did know for this low 5 device that it's very low power. Okay, so reading the flash, read finished. We can close this, and now we can see here a little hex editor view. It turns out there's the bootloader in the first section of memory, and then like way down below, there's the user code. But because this is 16 megabytes and the code is very small, it's mostly Fs, but then there's some data. So let's just do a quick, let's save this and see if we can view it in a different way, just to give us an idea about what's actually there. Save that as dump.bin, so file has been saved. So now this binary that we just extracted from that external flash device is in this binary. Here we can load it into hex editor, which gives us a similar view, right? Not super exciting. I don't remember where the code space starts, but if we're going to reverse engineer the chip, you could actually take this binary file and throw it into Ghidra, so the open source reverse engineering tool created thanks to the NSA, and other reverse engineering tools, dealing with RISC-V support. But what I like to do, if I extract some data from a device, the first thing I generally do is just run strings, which is a command that's going to show us printable ASCII. So I'm going to run strings, and I'm going to set it to only look at printable ASCII characters in words greater than 6, because a lot of times regular non-ASCII bytes still look as printable ASCII, or like you will see in the hex editor, there's like, B.CZS. Like that's not really useful for us. We want to see things that are longer and potentially more useful. So I can just drag that in, and we'll run strings, and it looks through that entire 16 megabyte blob and pulls out, some cool stuff here. Low 5 bootloader jumping to whatever the memory address is. So this must be the bootloader stuff at the beginning of memory. And then this is the user code down here, this nice ASCII art logo. That's in my code when I had programmed these to have it print the logo and do some other stuff. So it's like, has some debug messages. Sometimes if we're looking through code that we've extracted, especially from, say, a Linux device or other things, we're going to see like potentially hard-coded credentials, passwords, network configuration, private keys, all sorts of things. This is just, I want to show ASCII art because, who doesn't like ASCII art? Okay, next. is going to be JTAG. So JTAG is an industry standard test and debug interface that's used a lot nowadays, not only for testing a system, but for programming and debugging. Some of us call it the root shell of hardware, because it's something that if you can get access to it and it's exposed and not protected with any sort of security mechanism, you have complete control of the system, of that hardware. So it's pretty awesome. So what I'm going to do is stop sharing my screen again, go back to the camera view, and set up the next experiment. I have two JTAG experiments. The first one is using a tool called the JTagulator. This is a tool that I designed a bunch of years ago, and I'm still updating it with firmware updates and stuff. That is intended to help you identify the correct JTAG pins of a device. Now, JTAG is a multi-pin interface, so it has a minimum required 4 pins that you need to find. Sometimes there'll be more as well. So there's a lot of permutations a lot of times if you don't know. Like on this system here, I'm using an HTC One X phone. There's a little piece of tape here, but there's all these wires. There's like an unpopulated connector right at the edge of the board. That's a good indication that it's, you know, a programming interface or test interface or whatever. So we can tap down onto those and hook up our tool and identify those pins. And then once we identify those pins, we would go to the next step, which will be the next demo. So I have the JTagulator set up. This is just powered by USB. I'm going to switch over to, I think I was using CoolTerm for that as well. So I'm going to have to, I think I can use PuTTY. Oh, I'm not sharing my screen. Okay, I'm going to go to share my screen. Close what I had here. I think it actually connected the JTagulator in Windows, so I'll just stay in Windows. Oh.
Nope, not seeing it.
Okay, should be coming. Looks like it's kind of slow.
Okay.
Yeah, there it is. Okay. All right, so now I'm in Windows. It looks like, yeah, it looks like JTagulator is set up. It shows just as an FTDI USB to serial adapter. So let's see, I think I'll just use the Parallax terminal program here just because I have it. This sort of shows you, like, if stuff doesn't always work, this is the beauty of hardware hacking, right? It's like you just have to figure it out. Okay, so Parallax Serial Terminal is part of the Propeller tool, which is what I use to develop the JTagulator, but it's just another terminal program. With the JTagulator, I should be able to hit any key. I can get the menuing system. I'm not going to show a huge amount here because we have a lot of other stuff to do, and there's plenty of videos and demonstrations about the JTagulator online. What I did forget to do is plug in the phone, because I need to power the phone also, because the JTagulator isn't powering it. So I just plugged in a mini USB cable, or a micro USB cable for that. We have to set our target voltage because the phone operates at a 1.8 volt level, and the JTagulator can handle anywhere from 1.4 to 3.3 volts. So we want to make sure our voltage levels are correct so we're not frying anything when we're talking to it. Go to our JTAG menu. You can see there's a lot of other functionality as well. But all we want to do now is identify those pins, because then we can use more proper JTAG hardware for our other attacks. So here we're going to enter the number of channels we have set up. I think it's set up on channel 1 to 7. And I'm just going to start the scan. And if we're lucky, yes. Okay, so pretty much right away, we see the results. TDI, TDO, TCK, and TMS. Those are the 4 required pins of JTAG. We see device IDs. Those will help us indicate if we don't know what type of chip we're working with. You could search those online, these device IDs, and actually get information about the chips. Oh, it's a Qualcomm chip. It's whatever. We can also like test the interface to make sure we can communicate with it properly. This board also has a JTAG pin called RTCK, which is used for higher end systems. So we can actually test RTCK as well, which is an optional pin. Let's see, is the clock already known? It is. We just detected it as 5. It's going to check those and check for this additional return clock. And now we have all the pins that we can go and hack on a system, which is cool. So I'm going to end screen share. That is the fastest JTagulator demo I've ever given. So I'm going to close up some stuff on my screen and bring us to the next demo, where now that we know our pin out, in theory, we would use the same device and then connect some other hardware to it. But again, I want to use lots of different things. So here I'm going to bring a different device. This one is an Intel Galileo. It's an x86 little board running Linux. And this, we already know what the JTAG pinout is because it has a handy connector that says JTAG, and it's a standard ARM connector here. So if we didn't know, we would use the JTAGulator, find the pinout, and then connect a tool like this one, which is the Tigard, which is a general purpose kind of serial device hacking tool by Joe Fitzpatrick. And this, I believe, is available on Crowd Supply. It's an FT2232H based device, which works with a lot of different software. And I'm going to clobber Joe's quote, but he had said, we were talking about this, and he's like, there's no point in having complex hardware when you can have complex software. So the hardware interface is very simple and just has what we need. And then it supports all sorts of different software tools through that FT2232 to do JTAG communication, to do logic analyzer, to do SPI and I2C and memory reading and stuff. So this is a great little device. So we have our device here. I'm going to plug it in. I have another FTDI friend connected to the UART interface. And then I need to get the Tigard plugged in as well. So this is kind of going to be off the screen a little bit. So Tigard is our JTAG interface. And then our FTDI friend is the UART interface. I like to think of the UART as kind of the front door and JTAG as the back door. All right, so I'm going to share my screen again. Wait for that to come up.
Hey, Joe, while we're waiting, just we're going to go a few more minutes, and then we'll take some audience questions. So I just wanted to give everybody a heads up on that.
Yep. All right. So I'm going to blast through these because they're fun, and then we'll try to answer as much as I can. So I had to reload PuTTY because that cool term broke. So I'm at 115.200. Okay, so I'm going to connect to the front door of this Galileo device. And let's see, I'm going to power cycle the board. We should see some data on here if I got it right. Okay. So we are booting the Galileo. And actually, maybe while we're doing that, I'll get the other demo set up. Move this over here. It's funny, everything takes longer when you do it live instead of just on your own. Okay, so we're booting and we're seeing all this UART information, just like we saw on those other boards. And we're going to log in to the system once it boots. This example here is using JTAG for basically privilege escalation. So patching memory while the system is operating in order for us to get access to something that we wouldn't normally have access to. So here I'm going to log in as, geez, what is my password? I think it's guest with no password. Okay, so I'm in. And if I try to read the etc shadow file, this example, by the way, is courtesy of Joe Fitzpatrick. He and Matt King gave a presentation at Black Hat called JTAG Exploitation. And so this one's based on that. So we can try to read the shadow file, permission denied. We can't because we are a normal user. And now we can use the magic of JTAG to connect up, patch that access control check, patch that function that's checking, to see if we have permission, and then let us read it. So let's see how fast I can do this one. All right, so now we're in. So we're going to use OpenOCD to connect to the Tigard, to the Galileo. And now we see we're connected. Then on my next window is going to be our interactive window over here. Move this out of the way. Okay, so from here, we can actually take a look at the system we're connected to. We can halt the system. So now we're controlling the microcontroller on that Galileo. Need to pop open another window. Now we're going to use GDB. So GDB is the GNU debugger. We can communicate through the GNU debugger, through OpenOCD to the hardware. So if you're into software, this might be pretty exciting. So now we're going to load GDB. We're going to connect to OpenOCD. Now we're in. We're going to set a breakpoint. So again, this is stuff that you would have to do a lot of legwork in advance to know like what you want to do and where you want to do it. But I'm going to set a breakpoint on the function before it returns. And then we're going to end up patching that return value to say, yes, we have permission. So I'll set a breakpoint. We're going to continue execution. So now I'm back here and I can type. So let's try to read the SC shadow file again. And now we've hit our breakpoint. So we're actually hitting that function. If we look at like info reg, we can see the register EAX as our return value. That's -13 or F3. We want that to be 0 to tell the system, yes, we have permission to read that file. So let's change that to 0. And this is all through JTAG, by the way, right? So that Achilles heel or that root shell of hardware. So we're going to set that. We're going to delete our breakpoints. We're going to continue. As soon as I do this, we should see the shadow file if this works well. So 3, 2, 1. Ta-da. And here's our shadow file. And here's actually our root with our password hash. Now we can go and use John the Ripper or whatever to go crack that password. So that's a cool, quick example of JTAG. And I have 2 more. One of them I'll do really fast. The other one I'll answer questions while I'm getting it set up because that is worth doing. I do know actually one of the questions was about different types of hardware that you can use for hardware hacking. Hopefully this one, this demo or this presentation kind of gave you some examples of that. I will show you some others as well. Once I go back here. Oh yeah, okay. So we have things like some stuff I didn't show. So the Glasgow is a digital interface explorer, sort of general purpose, high-end type of device where it has an FPGA and you can do all sorts of crazy Python communication to control hardware. That's on Crowd Supply right now. There's the Bus Pirate. There's Hydra Bus, more general purpose devices. If you're dealing with USB, there's the Face Dancer. There's the Phi Whisperer USB that you can sniff communications on the USB bus, which is typically harder to do on, say, an oscilloscope. We have different types of fault injection devices. So the one I'll show is this one here, is the Chip Whisperer made by Colin O'Flynn. We also have the chip.fail glitcher that was released at Black Hat the last physical Black Hat. So this is a little multiplexing switch. If you're doing wireless, there's the Hack RF, there's the Bluetooth Ubertooth 1. So there's all these different open source tools that are available to kind of hack on stuff depending on the system that you're working with, which is kind of cool. And it's the power of the community, and it's stuff made by hackers for hackers, and really kind of shows the strength of this industry and of this community. Okay, so I have this device. This is more advanced. This is called voltage glitching. And what we're doing is basically this microcontroller has some code in it. There's code protection to prevent us from reading the contents out. So if we did put it in a device programmer, that wouldn't work. So we're basically tricking the system and causing this to corrupt a read during the boot process to skip over the check or to invalidate the check of saying, hey, is this chip supposed to be protected or not? Because as the boot ROM in the chip loads up, it reads the state of a register. There's 4 valid values for this particular chip. It's an LPC 1114. And a lot of the LPC family is also vulnerable. But if you can glitch that, those 4 values are stored in a 32-bit register, which is 2 to the 32, right? There's 4 billion possibilities and only 4 valid ones. So if we can glitch that at just the right time and skip over that check, all we have to do is be one of those other 4 million or 4 billion, and it's going to let us read the code. So I'm going to power up this board. I have the Chip Whisperer Lite set up here. I'm going to plug that in. And Chip Whisperer Lite is a piece of hardware that lets us use Python to cause misbehavior in different types of devices. So it's a really, really nice way to deal with voltage glitching in these very complex types of things. So I'm going to share my screen again and find my window. Okay, so let's wait for it to come up. What I'm showing here is a Jupyter notebook that Colin O'Flynn made for some demonstrations up the Chip Whisperer using the LPC 1114. This original work was done by Chris Gerlinski, and then Colin O'Flynn made this nice Jupyter notebook to kind of go through it using the Chip Whisperer. So I'm just going to run through step by step. So it's going to do the setup, set up the chip whisperer, set up the chip whisperer with some of the settings that we need for the speed. And how we want to glitch the system. We're basically looking at the reset line, forcing the chip into bootloader, and then as we reset the system, we wait a certain amount of time and then cause a glitch to happen on the reset line. If we had more time, I would show you, what that looks like on the oscilloscope. I did tweet a picture of that earlier on. Let's see, okay, so we set that up. So everything is set up now. Now we can go and try to communicate with the chip. Make sure that's all set up. And if you do have a chip whisperer, this fuse bypass example is on the chip whisperer GitHub repo, so you can do all of this stuff yourself. It's running awfully slow, which I think might be because I kind of messed up my USB interfaces and stuff earlier. That's a bummer.
But maybe on that note, we may want to just kind of wrap up, answer a couple of questions, do some housekeeping, and let our audience know that perhaps you'll be able to follow up with some people with some of their questions.
Yeah, okay, so the demo is working. Sorry, let's see if we can just get through this one. So we're communicating. When we try to read, though, from the device, it says, nope, you're not allowed to. Like, we can't read from memory because we get an error because it's locked. Now let's just do the quick glitch. We're going to set it up, and we're going to run, and it's attempting. We can see on the screen it's trying different time offsets from the start of memory and different widths of the glitch, and it's normal. Hopefully we'll get to a point where it actually, oh yeah, so look, success. So now we've actually defeated the code protection that's preventing us from reading the chip. Now it's dumping all the code, and that's it. So yeah, this is probably a good time to end. The other example I do have, the last one, is the electromagnetic fault injection, which looks like this. Colin O'Flynn made a device called the Chip Shouter, which is it's really heavy. Another device that lets you do this fault injection, and you need to have like very precise control and movement of the system. And this is a contactless way of doing fault injection. So you don't need to wire stuff up or modify the target board at all. You can just blast it with electromagnetic interference at certain points on the chip and cause the same sort of behaviors. So this demo I won't show. Colin has some interesting work on this, and it's a really fun, advanced topic. And it just sort of shows, all of the different stuff that you can do. So that is it for me. Let me switch back to my face for a second. I do want to thank you for sitting through this. I know we did a lot, and that was the intent of just trying to cram in like all of this stuff, just to show you what's possible. And you can see sometimes things don't work as well. Sometimes they do. That's the beauty of hardware hacking, and I hope you get into it. So I will be right back.
Okay, outstanding. Thanks very much. This was fun. A lot going on. We want to thank everybody for attending. We've got a lot of questions. Joe may be able to answer one, but we're going to give him your contact information, and he could follow up. We have a poll question that we put in front of you if you want to give us some feedback on what you thought of today's event and future events. We have a feedback survey that we'd also appreciate getting some insight into what you thought of this event a little bit more in depth and how we can improve on this and others in the future. So unfortunately, Joe, that is going to be all the time we have. And I'll show here on our audience some ways to contact you and show all of that. And again, alert everybody that our next webcast is on May 6th, and it's entitled Stealing the Silver Lining from Your Cloud. So we'll push out a link and you can register. And we want to thank you all for attending today's Black Hat webinar, Hardware Hacking Party Tricks, Techniques for Exploring, Manipulating, and Exploiting Embedded Systems, brought to you by Black Hat and Informa. And shortly after this live event, we'll send you an email so you can access this presentation on demand. And on behalf of myself and our guest, Joe Grand, We want to thank you all for your time and have a great day.
Thank you.